Dear children, have you ever wondered what holds the moon in orbit and makes apples fall to the ground?
We know that this is due to one of the fascinating forces existing in nature, which was discovered by the English scientist Sir Isaac Newton. The force of attraction by which the earth attracts all objects towards itself is called gravitational force, and this is the reason why the apple falls towards the earth. Today we are going to study how the gravitational force of attraction works between different objects. Let us consider two objects with mass m1 and m2 separated by a distance d meters. According to Newton's law of gravitation, the force of attraction between two objects is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So accordingly, we can write force is directly proportional to the product of masses, which is m1 into m2. Also, the force is inversely proportional to the square of the distance between them. So we can write F is inversely proportional to d square. Combining these two equations, we can write it as F is proportional to m1 into m2 divided by d square. So here we have to change the proportionality sign. So F is equal to g into m1 m2 divided by d square. Here J is a constant. This equation is popularly known as the Newton's universal law of gravitation. F is equal to g into m1 m2 by d square. Here g is the gravitational constant having a value of 6.67 into 10 raised to minus 11 Newton meter square per kilogram square. So let us find out how the mass of the bodies and the distance between the bodies affect the gravitational force of attraction between them. In case 1, let us consider two bodies having masses small m and capital M, and they are separated by a distance d. The force of attraction between these two bodies according to Newton's law of gravitation can be written as F is equal to g into mm divided by d square. F1 denotes the case 1. In second case, let us consider a quite larger body in the first position, which is having a mass of 2m than the first case, and the second body is having the same mass as that of the first case. And the distance between these two bodies remains the same, d. Here the force of attraction between these two bodies is g into m into 2m divided by d square, which can be written as 2 into gmm divided by d square. If we compare it with the first case, we can see that it is twice the force in the first case. So when we double the mass of the body, we can see that the force of attraction between the bodies also doubles. Let's take the case 3. Here the mass of the first body is 2m and the mass of the second body is quite larger. I have taken triple times the mass of the body in the second case, and the distance remains the same. So we have taken 2 times the mass of first body and 3 times the mass of the second body. So here the force of attraction will be g into 3 into m into 2m divided by d square, which will be equal to 6 into gmm divided by d square. If we compare it with case 1, we can see that it is 6 times the force of attraction in the first case. So when we double and triple the mass of the bodies, the force of attraction will be 6 times the force in this first case. Let's go to the fourth case. Here I have taken masses same as the first case. What I have changed here is the distance between the bodies, which will become double the distance of the first case. Here the force of attraction can be written as gmm divided by 2d the whole square, where 2d is the distance. So which will be equal to gmm divided by 4d square. So if we compare it with the first case, we can see that the force of attraction became 1/4 of the first case. So if we double the distance between the bodies, the force of attraction will be 1/4 of the actual force. Okay, let's move to the fifth case. Here I have taken the bodies with the same mass as in case 1 with small m and capital M as the masses, but I cut down the distance between the bodies as d by 2, which means comparing with the case 1, the distance of the body is half of the first cases. So the force of attraction between these two bodies is equal to g into mm divided by d by 2 the whole square, which is equal to g into mm divided by d square by 4, which we can write as 4 into gmm divided by d square. So when we cut down the distance between the bodies by half, we can see that the force of attraction will become 4 times. Let's check the case 6. Here again I have taken the bodies with masses small m and capital M, but I have again cut down the distance between the bodies into d by 4, which means comparing with the initial case, now 1/4 is the distance between the bodies. Now the force of attraction will be equal to G into mm divided by d by 4 the whole square, which will be equal to gmm divided by d squared by 16, which we can write as 16 into gmm divided by d square. Comparing it with the first case, we can see that it became 16 times the force of the first case, which means if we cut down the distance between the bodies by 1/4, the force of attraction will be 16 times the force in the initial case. Now you have understood the effect of mass and distance on gravitational force. What is the gravitational force experienced by humans? Let us find it out through a problem. Here, two children are standing apart at a distance of 2 meters, and one of them is having a mass of 50 kg and the other is having a mass of 45 kg. Let us calculate the gravitational force of attraction between these two children. So we'll pull out the values first. One of them is having a mass of 50 kg, other is having a mass of 45 kg, and their distance is 2 meters. We know the value of gravitational constant as 6.67 into 10 raised to minus 11 Newton meter square per kg square. And according to Newton's law of gravitation, the force between them will be equal to G into m divided by d square. So we will insert the values. F is equal to 6.67 into 10 raised to minus 11 into 50 into 40 divided by 2 square Newton. So this will be the value of the force of attraction between them. Upon calculating, we'll get the value as 3.335 into 10 raised to minus 8 Newton. So we can see how so small the value is. From this we can find out that the force of attraction between humans is very feeble and they are not capable of other forces like frictional force, magnetic force, etc. That is the reason why we are not experiencing any gravitational force between humans. So the next time you drop something or gaze at the moon, remember the Newton's universal law of gravitation is quietly at work, connecting each and every object in the universe through an invisible force. That's all for the day. Thank you.